everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today, I want to discuss about the question bank of corrosion, related to this engineering typology subject. So already in previous sessions we have discussed about corrosion and then definitions and terminology related to this corrosion topic. And in this session, the long answer type questions related to this corrosion. How to attempt this type of questions we will see. In examination point of view, suppose sometimes they will ask questions long answer type and short answer type and critical thinking type questions. So in this session, we will discuss about this long answer type questions, the question bank of corrosion. The topic is, sometimes they will ask the differentiate between dry corrosion and wet corrosion. So already we have studied about dry corrosion and wet corrosion and other types and prevention methods. But in this particular question, you have to give answer difference between these two. So what is dry corrosion and what is the wet corrosion? So which one is advantage? What are the advantages and disadvantages? And then how to control prevention methods? How to write elaborately. So in this, first, the definition, the dry corrosion. So as per definition, the dry corrosion, also known as chemical corrosion, occurs in the absence of a liquid electrolyte. It typically happens in gaseous environments. So the mechanisms involves direct chemical reactions between the metal and gases. So in the environment. So the dry corrosion is also known as chemical corrosion, and there is no need of the liquid electrolyte like water and other solutions. It happens, this type of corrosion happens in gaseous environments. Whenever the surface is involved, directly exposed to environment, between this, the chemical reaction involves between the metal and the gases. What are the gases present in the environment? The common reactions include oxidation, sulfidation, and halogenation. So what are the conditions? Typically occurs at high temperatures and no presence of a liquid phase. So already I told you there is no electrolyte function. Examples: oxidation of metals at high temperatures in air or oxygen, sulfidation in environments containing sulfur gases, halogenation in the presence of halogen gases, example chlorine. The products, formation of solid corrosion products such as oxides, sulfides, and halides. These products can form a protective layer, example chromium oxide and stainless steel, or be non-protective, that is iron oxide and carbon steel. So these are the products. So whenever the oxidation of metals at high temperatures in air or oxygen, the products can be protected from the protective layer, that is the chromium layer or chromium oxide layer on a stainless steel. And be non-protective iron oxide and carbon steel. So characteristics, usually uniform corrosion occurs across the surface. Corrosion rate can be influenced by temperature, gas composition, and metal properties. Often forms a thin continuous film on the metal surface. These are the characteristics. Next, prevention methods. Use of high temperature alloys and coatings. Environmental control to reduce exposure to reactive gases. The application of protective oxide films, example aluminizing and chromizing. So these are the prevention methods. use of high temperature alloys and coatings. By using these type of high temperature alloys and coatings, you can control the corrosion. And environmental control, reduce the exposure to reactive gases. You can use protective films. Next, wet corrosion. So in the case of wet corrosion, so definition, wet corrosion, also known as aqueous or electrochemical corrosion, occurs in the presence of a liquid electrolyte, typically water. The mechanism involves electrochemical reactions where metal atoms lose electrons as oxidation and become metal ions. That requires the presence of an electrolyte to facilitate ion and electron transfer. Formation of anodic and cathodic regions on the metal surface. So as per definition, they occurs in the presence of a liquid electrolyte. In the case of previous corrosion, in dry corrosion, there is no presence of liquid electrolyte. Chemical reactions between the metal surface and gases present in the environment only, in the case of dry corrosion. But in this wet corrosion, not like that. It occurs in the presence of electrolyte. So where metal atoms lose electrons, that is the oxidation, electrons become metal ions. So already we have seen in the previous sessions chemical reactions. Conditions typically occurs at ambient or moderate temperatures. The presence of liquid phase, water or other electrolytes. Examples, rusting of iron in water, galvanic corrosion between dissimilar metals in an electrolyte, and fitting corrosion in chloride containing environments. So these are the examples for this wet corrosion. The products are formation of hydrated corrosion products such as rust, iron oxide or hydroxide. Products can be loosely adherent and non-protective, leading to continuous corrosion. The characteristics are can be uniform or localized, fitting or career-wise corrosion. The corrosion rate influenced by factors such as oxygen availability, pH value, and electrolyte composition and temperature. So involves electrochemical cells with anodic and cathodic areas. These are the characteristics. How to prevent? The prevention methods are use of corrosion resistant materials and alloys by the application of protective coatings like a paint and galvanization, cathodic protection. In cathodic protection, one is sacrificial anodes and impressed current systems. Already we have studied about these two methods. Use of corrosion inhibitors in the electrolyte. Design considerations to minimize careways and ensure proper drainage. So by applying these methods, you can prevent the dry corrosion or wet corrosion. So next question is explain the performance and selection criteria of fitting corrosion. So what is this selection criteria for fitting corrosion? The fitting corrosion is a localized form of corrosion that results in small but often deep fits on the surface of metals. It can lead to significant damage and failure of structures, even if the overall metal loss is minimal. So the significant The small cracks initiation on the surface of the metals can lead to significant damage and failure of the structures. This type of corrosion is called as fitting corrosion. The selection criteria is one is material selection, alloy composition. Criteria: choose materials with alloying elements that enhance fitting resistant. The performance is alloys containing elements like chromium, molybdenum, and nitrogen. Example: stainless steel offer better resistance. Next example, the 316 stainless steel with molybdenum composition is more resistant to fitting than 304 stainless steel. These are two materials, different materials. The alloy composition is different. The 316 stainless steel alloyed with molybdenum. Another one is 304 stainless steel is resistant. The 316 stainless steel more resistant to fitting than this 304 stainless steel. So in the example, in stainless steel, the alloying elements are molybdenum or chromium or nitrogen. Microstructure criteria: materials with uniform and fine-grained microstructures are preferred. Fine grains reduce the initiation sites for fits and provide better overall corrosion resistance. The surface condition, the criteria is smooth, clean surface are less prone to fitting. The performance is polished surfaces reduce the number of crevices and sites where fits can initiate. So the surface condition always should be in a smooth and a clean surface. So it gives less prone to fitting. So the fine grains reduce the initiation of sites for fits. Next, environmental conditions. In environmental conditions, chloride concentration. Criteria: use materials resistant to chloride, induced fitting in environments with high chloride concentrations. The performance: materials with higher fitting resistance equivalent numbers perform better. Example is titanium and nickel based alloys in seawater environments. The seawater environment that contains the titanium and nickel based alloys. So in this, the chloride concentration is very more. They use this material resistance to this chloride induced fitting in environments. Next, pH values. So criteria is consider the pH of the environment where the material will be used. So next, the performance is metals like aluminum are more prone to fitting in acidic or alkaline environments. The temperature. Next factor is temperature. The temperature criteria: high temperature can accelerate fitting corrosion. Select materials accordingly. So high temperature can accelerate the fitting this type of corrosion. So by selecting while selecting the material, you should care. Remember these temperatures. Keep in your mind. So high temperature resistant alloys perform better in hot environments. So pH values and then temperature criteria is very important in this fitting corrosion. So next, design considerations. So while designing a component or product, so design to minimize crevices. the joining parts, curvature parts, undercurved parts, the sharp corners and areas where water can stagnate. So where water can stagnate, there is a corrosion. That corrosion is called as curvature corrosion. Performance designs that ensure proper drainage and fluid flow reduce the risk of pitting. The cathodic protection. In this, use cathodic protection in critical applications to prevent pitting. In above case, when designing the component, avoid the sharp corners. Minimize the crevices. In the case of cathodic protection, use the cathodic protection in critical applications to prevent the pitting. The performance is sacrificial anodes are impressed. Current systems can protect susceptible metals. So next, protective coatings and treatments. Coatings. Criteria: apply coatings that act as barriers to prevent exposure to corrosive environments. Performance: high quality coatings like epoxy, polyurethane, or metal plating, galvanization provide effective protection. Surface treatments. Use treatments like passivation to enhance the natural oxide layer. So in the case of protective coatings and treatments, coatings one and another one is surface treatments. The performance is treatments such as electropolishing improve the resistance of stainless steels to pitting. Next, maintenance and monitoring. Regular inspections. The criteria is schedule regular inspections to detect early signs of pitting. Performance. Early detection allows for timely maintenance and reduces the risk of catastrophic failure. The monitoring techniques. Criteria is use techniques like electrochemical noise analysis and pit depth measurement. Performance is advanced monitoring can provide real-time data on fitting progress. Corrosion inhibitors. Inhibitors are chemical inhibitors. Criteria is use corrosion inhibitors in the environment to mitigate fitting. So inhibitors like molybdates and nitrates can reduce the aggressiveness of chloride ions. Next question is briefly explain the advantages and disadvantages of anodic protection. So anodic protection and cathodic protection already we have studied. So here is asked here briefly explain advantages and disadvantages of anodic protection only. So anodic protection is a corrosion control method that involves making a metal structure the anode of an electrochemical cell to maintain it in a passive state. The advantages are effective for passive metals. Benefit: highly effective for metals that from a stable passive oxide layer. That is example stainless steel and titanium. The explanation is the anodic protection maintains the metal in the passive state, reducing the corrosion rate significantly. So main advantage effective for passive metals. The low current requirements requires less electrical current compared to cathodic protection for maintaining passivity. The explanation benefit is once passivation is achieved, only a small current is needed to maintain the passive field. Next advantage is protection in aggressive environments. So the effective in highly aggressive environments where other protection methods may fail. So the explanation is can protect metals in environments with high acidity, high temperatures, or high chloride concentrations. Cost effective for larger structures. The more cost effective for protecting large structures like storage tanks and pipelines. The explanation is lower current requirements translate to reduced energy cost over time. The long-term protection benefit is provides long-term protection with minimal maintenance once the system is properly set up. The explanation is stable passive film requires less frequent monitoring and adjustments. So disadvantages are complexity of control systems. Drawback, it requires a sophisticated control systems to maintain the correct potential. Precise control of the anodic potential is critical to avoid over or under protection. So limited to certain metals. Drawback is only applicable to metals that can form a passive oxide layer. So not effective for metals that do not readily passivate to, such as carbon steel without suitable alloying elements. Next, initial setup cost. High initial setup cost and installation and the setup of the aeronautical protection system is very costly. So requires investment in control equipment, power sources and monitoring systems. So potential for passive layer breakdown. Risk of passive layer breakdown under fluctuating environmental conditions. Changes in temperature, pH values, chloride concentration can disturb the passive layer leading to localized corrosion. Limited use in non-stationary structures. Not suitable for moving or transportable structures, not suitable this type of layer and this type of cathodic anodic protection method. So anodic protection systems are designed for stationary setups where constant monitoring and controls are feasible. So these are the references I have taken for this question bank explanation. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.